Now, boiling point and melting point, okay, we can look at the cis and trans isomers first. Okay, do remember, okay, even though you have the stereoisomers cis and trans, they are different. Okay, and then how different? Yeah, one of the qualities that they have is going to be, one of the property will be, they have different boiling point and melting point. Now, I just want to ask you, okay, I just want to ask you, if you have cis, okay, if you have cis and trans, which one do you think will have higher boiling point? Josh? Any idea? Just take a random guess.
From cis to trans.
Which one do you think higher boiling point?
Intermolecular forces, so trans.
Okay, let's look at this properly here, because do remember they have the same MR, the relative molecular mass. So the size are same. So intermolecular forces between them, they are almost the same. Okay, they are almost the same. But what is going to be different over here is you can see that if I have this example, this is going to be cis. You can see that the electron, okay, they are going to be pushed more towards to the top, because side by side, right? So they are going to push more towards the top, whereby the charges are more like imbalanced. The charges are imbalanced. And if you look at trans, okay, if they push over here, they pull over here. It's like they are going to be cancelled partially. Okay, we can look at it in that way. When they are cancelled partially, even though they have similar intermolecular forces, okay, but cis generally will have slightly polar because it's not symmetrical. Okay, because the dipoles, there is going to be some of the dipoles that are not cancelled. So they are going to be slightly polar. This is going to be less polar. Okay, so this is slightly polar a bit. Okay, a bit polar. Okay. So if it is boiling point depends on intermolecular forces of attraction. We have permanent dipole-dipole, we have van der Waals forces, we have hydrogen bonding. Now the thing that I want to look at is going to be in polar sense. So we look at permanent dipole-dipole. Yeah. So permanent dipole-dipole, if you look over here, this is more polar. So it is understood if I say why cis is going to have higher boiling point compared to trans, okay, because they have less intermolecular forces, the boiling point is less. Okay, can you understand this, Josh?
It
Okay.
this is a concept for polar molecules, right? Plus the arrangement that they're
Yes,
in
yes. So we
from
are
the
using
old
that
chapter.
concept to explain cis and trans. Okay, cis is going to be slightly polar. Okay, trans is going to be less polar. Therefore, okay, the boiling point is higher, boiling point is lower. Now, my question over here is, okay, let's ask Jordan. Jordan, do you think what will happen to the melting point? Do you think the boiling point is higher over here? What can you tell about the melting point?
Melting point, last time I heard it decrease.
Okay, so it's the other way around. Okay,
Yeah.
it's the other way around. One of the common mistake that everyone makes is they think the melting point and boiling point is going to be higher. If it is increased, they think it's going to be higher. It's going to be different. Yeah, it's going to be different. And I will tell you why it's going to be different. Because melting point depends on the packing, on the arrangement. Okay, on the arrangement. If you want to melt something, if you want to melt solid to become liquid, you are breaking the regular arrangement of the solid and you want to make it into liquid. So we need to look whether are they going to be compactly packed or they are going to be loosely packed. And if I try to represent this molecule in this manner, you can see I assume that Cl is bigger than CH3 and I draw in this kind of a diagram. And I'm going to draw trans in this way. And if I arrange them, you can see that, okay, they have a lot of empty spaces in between when I arrange them. Okay, but if I arrange trans, you can see that they have minimal space in between because they try to rearrange themselves. Okay, they can rotate and so on. and they will have minimum space between them. So this is going to tell us that, okay, your cis isomer, they are going to be less compact. When they are less compact, your melting point is going to be lower. It's going to be easier to separate them. Okay, it's easier to break them. And if it is more compact, okay, the melting point is going to be higher because it's going to be more difficult to separate them, because there's going to be a lot of forces that is taking place over here. I need to supply a lot of heat. Okay, so this is what I want you to remember. Okay, boiling point for cis is going to be higher. Melting point, on the other hand, is going to be lower. It's the other way around. Okay, now you can apply the same concept for branched hydrocarbon and unbranched hydrocarbon. Okay, you can apply the same concept. How? Okay, branch hydrocarbon. You can see here, okay, I have the same number of carbon over here. 1, 2, 3, 4, 5, 5 carbon. One, I have a long hydrocarbon chain, and I have another one that is going to be branch. And if you look at the branch, the way it is arranged, I will put it as a circle. It looks like a sphere. Okay, it looks like a sphere. And this is going to be more like oval shape. Okay, because it's a bit elongated. Now, if I use the same concept over here, I want to see whether branch or unbranch, which one will have higher boiling point or melting point and so on. So the same concept, I am going to look at boiling point. Now, boiling point, now it depends on the, again, intermolecular forces of attraction. But here, it is much more better if we can look at it instead of polar or non-polar. We look at it in terms of total surface area. Now, if you look at the total surface area, the one that I've highlighted in red color over there, if it is going to be spherical, you can see that the total surface area is going to be less. Okay, please remember this. The total surface area between other molecules are lesser. If you look at this one, the one oval elongated a bit, you can see there is more surface area, more point of contact. If you have more point of contact, okay, it means you have more intermolecular forces. Therefore, the boiling point for unbranched is higher. The boiling point for branch is going to be lower. That is going to
Sir,
be the explanation. Yeah, Josh.
does this concern van der Waals forces?
Yes, it is concerned van der Waals forces. So you see, intermolecular forces, we have permanent dipole-dipole, van der Waals, and hydrogen bonding. So here we are not talking about polarity. So we are not talking about hydrogen bonding. So only thing that we are going to talk about is your van der Waals forces. Depending on the, when we say total surface area, means the point of contact whenever the electrons can be rearranged at one side. So this is van der Waals forces. Okay, but okay, I want you to just learn about how to differentiate. That is very important. Now, how is it going to be applied when it comes to melting point? Now, again, earlier I told you melting point depends on the arrangement or the tight packing. So here, when I arrange all the spheres, okay, I can see there is going to be a regular arrangement. But when I arrange the oval structures over there, you can see that they are loosely packed. When they are loosely packed, melting point is lower. When they are tightly packed, the melting point is higher. Okay, so in summary, what we are going to what we have learned. Okay, so in summary, I have taught you about cis and trans. Cis will be slightly polar. Okay, slightly polar because the dipoles are not cancelled, and therefore because they are polar, because the intermolecular forces are there, the boiling point is higher. Now, when I want to talk about melting point, cis, okay, the way they are going to be arranged is going to be something like this. You can just roughly guess like this, okay. So this will take a lot of space, okay, in comparison to if I'm trying to arrange it in this way. Okay, so this will be more compact, okay, and if it is more compact, the melting point is going to be higher. The same concept I try to apply with the branch and unbranched. Branch will have more spherical shape. Unbranched will have less spherical shape. Okay, so you are going to have this kind of situation. And then the branch, okay, because they have if you have a lot of circles around, there will be less surface area, boiling point will be less. But here, okay, because of this oval shape, it's going to be less spherical, more surface area, more boiling point because more van der Waals forces of attraction. But when we look at the arrangement, okay, the branch will have a more compact arrangement where this will result in higher melting point, and unbranched is going to be less compact and it will result in lower melting point. Okay, this is going to be the lesson for today.